Hi, and welcome to our air pump system demonstration video. In this video, we're going to demonstrate how the Conjecture System Identification software tool can be used to improve control on a PID-controlled industrial process. We'll illustrate such a process using a PID-controlled air pump system. This system consists of a 2-meter-tall clear acrylic tube in which we want to suspend a ping pong ball at a given height. We do this by pumping air up the tube using a motorized pump and varying the pump speed using a PID controller. Our input to this system, therefore, is the pump motor speed, going from 0 to 100%, and our output is the ball height within the tube in centimeters, measured by an ultrasonic sensor located in the bottom of the tube. Ball height data is fed back through the PID controller to vary the pump speed. So we would run our motor at varying speeds and collect data on our ball height at each point. This is a plot of the data that we got, with our input in red and output in blue. Because our system is nonlinear, we applied a 0.7th root power to the input and took the derivative of the output. We cover the reasons for this in more detail in our user training videos for Conjecture. But for now, this gives us input and output data that correlate better for modeling. So we take our input and output data in a CSV file and run it through Conjecture to find a best fit model. After trying a few models, we find that a delay of 3 gives us the best model. We'll go through the process of finding a best fit model in our user training series. The next step is to remove delay from our model, which will make it easier to program and more stable when we integrate it with our PID control system. We can integrate our conjecture model with our process using a complementary filter to artificially remove noise and delay from our process feedback. We use a standard complementary filter equation to integrate our conjecture model into a traditional PID process. Our model uses the results of our best fit equation drawn from conjecture, and our model output uses the change in ball height consistent with our process. Our complementary filter allows us to vary the ratio of process to model that goes into our PID controller. Here we've chosen a ratio of 0.2, 20% process and 80% model. And now we'll compare the performance of the system when we incorporate the conjecture model compared to having no model at all.
Here we have an air pump system under PID control using a complementary filter. And our conjecture model is here. Our set point of the ball is set to 100 centimeters, and we have a somewhat aggressive PID controller. Watch our system as it handles a set point change from 100 to 150 centimeters. So I'll just hit run. Now if I add a disturbance and block the pipe a bit, look at how it reacts. Quite stable. Now we change the set point back to 100. And we're going to have a look at how the data is trending here. So you can see here we made our set point change from 100 to 150. The disturbance point was here, and then this is our set point change back to 100. Now we're going to go ahead and change this complementary filter to process only. So this is typical of a normal industrial process. And as we did before, we're going to change the set point to 150. And also going to add a little bit more disturbance. As you can see, the process is very unstable. Let's have a look at this trend. So you can see we've done the same experiment here. We've had a set point at 100, changed to 150, add a little bit of disturbance, and back to 100. And you can see when we have the complementary filter added, the motor speed doesn't vary as drastically as when it's normal, just a normal bare bones PID controller.
So, how does this improvement translate to industry? Well, this means we can open and close our valves less. We can reduce the amount of acceleration and deceleration of our conveyor belts drastically. All of which is going to make your equipment last longer, and this can save on operating costs. It will reduce your wastage, improve profitability, and improve productivity.
For further information on Conjecture System Identification, visit our website at systemident.com and get in touch with us by email for a trial. Thanks for watching, and we hope you enjoy using Conjecture System Identification.